To understand edge computing, we need to reflect on the rise of the cloud. In recent years, cloud computing has been one of the biggest digital trends and involves the delivery of computing resources over the internet. In the early days, most of the devices that accessed cloud services were PCs and other end-user hardware. But increasingly, devices accessing cloud services are also Internet of Things or IoT appliances that transmit data for analysis online. Connecting cameras and other sensors to the internet facilitates the creation of smart factories and smart homes. However, transmitting an increasing volume of data for remote, centralized processing is becoming problematic. Not least, transmitting video from online cameras to cloud-based vision recognition services can overload available network capacity and result in a slow speed of response. And this is the reason for the rise of edge computing. Edge computing allows devices that would have relied on the cloud to process some of their own data. So, for example, a networked camera may perform local vision recognition. This can improve latency, or the time taken to generate a response from a data input, as well as reducing the cost and requirement for mass data transmission. Staying with our previous example, let's consider more deeply the application of artificial neural networks for vision recognition. Today, Amazon, Google, IBM and Microsoft all offer cloud vision recognition services that can receive a still image or video feed and return a cognitive response. These cloud AI services rely on neural networks that have been pre-trained on data center servers. When an input is received, they then perform inference, again on a cloud data center server, to determine what the camera is looking at. Alternatively, in an edge computing scenario, a neural network is usually still trained on a data center server, as training requires a lot of computational power. So, for example, a neural network for use in a factory may be shown images of correctly produced and then defective products so that it can learn to distinguish between the two. But once training is complete, a copy of a neural network is deployed to a networked camera connected to edge computing hardware. This allows it to identify defective products without transmitting any video over the network. Latency is therefore improved and the demands on the network are decreased, as data only has to be reported back when defective products are identified. This scenario of training a neural network centrally and deploying copies for execution at the edge has amazing potential. Here I've indicated how it could be used in vision recognition. But the same concept is equally applicable for the edge processing of audio, sensor data, and the local control of robots or other cyber-physical systems. In fact, edge hardware can be useful in any scenario where the rollout of local computing power at the extremities of a network can reduce reliance on the cloud. One of the challenges of both the Internet of Things and of edge computing is providing an adequate network connection to a vast number of cameras, sensors, and other devices. Today, the majority of devices connected wirelessly to a local network communicate directly with a Wi-Fi router. However, an alternative model is to create a mesh network in which all individual nodes dynamically interconnect on an ad hoc basis to facilitate data exchange. Consider, for example, the placement of moisture and temperature sensors in a large industrial greenhouse. If all of these devices have to have direct wired or wireless connectivity, then a lot of infrastructure would need to be put in place. But if the sensors can be connected to edge computing devices that can establish a mesh network, then only one wired or wireless connection to the local network may be required.